Yes, good evening, everyone. Again, today, uh, yesterday, if you remember, we are doing a one-dimensional problem. So today, we'll try to model this beam.
On my side
Uh,
process.
so here will be we'll try
I
to
cannot.
model this. Yeah, Jib sir, I think you are unmuted. Yeah, now it's fine, I guess. So today we'll try to model a three-dimensional beam. Okay, so we'll try to model this three-dimensional beam. So the beam dimensions are, again, it's a very simple cantilever beam. Yesterday we have seen this beam, right? This one-dimensional beam. Uh, where is this? Yeah, this is our yesterday's analysis. So in yesterday's analysis, we have just given a cross section, but now we'll also sketch the cross section. We'll also try to draw the cross section of the beam, and then we'll analyze that beam. In the previous one, if you remember, we are only getting the uh, stresses and strain values at each cross section, but within the cross section we are not able to get any stress and strain variations. But in this, we'll try to analyze this beam, and we'll try to get how the cross section, even in the cross section, like for example, how within this cross section how the stresses are varying. Even this we can see using this problem. So uh, whoever is having the software installed, they can just try to follow what I am doing. And if I'm if you're not able to follow in between, you can just stop me, so that I'll explain that step again, so that we'll both be on the same page. So once again, I'll sorry. So I'm opening this software again, ABAQUS CAE. So in this, I'm not again. If you see, the inputs are given straight away. Uh, the material, again, I'm taking it as a steel, again, for just for our convenience. And the length of the beam, I'm taking it as 200 mm. See, I actually, it was slightly a bigger beam, but because of our restriction, the limitation to 1000 knots, I made it slightly smaller. This is a 10 mm by 10 mm rectangular beam. The length is about, sorry, this is a square beam, so the length is about 200 mm. It has fixed support at one end, and other end is free, so this is like a cantilever beam. And here I'm not referring to any P or any load over here. So we'll just keep on giving some loads, and we'll try to get deflections over here. So uh, so let us start modeling this. So again, this is our the graphical GUI. The first step is we'll start to model the part. So in our part, the part which we have considered in this example is a rectangle, is a square beam, right? So go to this create part icon, press onto that. Meanwhile, I'll just try to know how many guys have installed. So Abhishek says he installed it, and Burhan also installed, and Raghu is having it. And what about others? You can just message if you have installed or if you haven't installed. Okay, fine. Then I'll go ahead. So part one, I'll write it as a square beam. Name as a square beam. Modeling space. This, see, yesterday we were taking it as a 2D planar because it's a one-dimensional kind of a beam. But here we actually wanted to model an entire three-dimensional geometry. So I am clicking onto this 3D modeling space. Type, again, it is deformable because it has to deform. If it is rigid, then there's no point of giving loads, right? So here it is. We need to give this as a deformable one. Then the next one is the base feature. The base feature will be solid again. Yesterday, if you remember, the base feature was wire. Wire is nothing but a line element. It's a linear element. So today we want it as a solid because we wanted to model a three-dimensional beam. Shape is solid. Type, it's extrusion revolution sweep. So this, I think, if you have some idea about your AutoCAD, you might be knowing about this revolution and sweep. Right now we only need an extrusion. So extrusion is something but you draw a cross section and you'll extrude it along the length, and you will get it, and you will get what you actually require. So this, I'll just keep it as 2000, and I'll say continue. So I'll get this interface where I can sketch my beam here. So I wanted to draw a rectangle. So yesterday we were using this create isolated point, and we are creating a lines joining those points. Now I wanted to create a rectangle. So what I'll do is I'll click on this one corner of the rectangle. So this midpoint, this is the origin. So 0 comma 0. So our rectangle is of size 10 mm by 10 mm, right? So for that, what I'll do is I'll make minus 5 comma 5 as one corner, and the second corner will be 5 comma minus 5. So you can see this part here. I'll be entering this. So please let me know if you're not following. I'll just repeat this, because if you skip one step, if you're not able to follow one step, then you will not be able to follow subsequent steps also, right? So you just let me know. I'll stop and I'll again explain it to you. So
Once again.
yeah. So what again, I'm just clearing this out. So again, create part. I'll just give it as a square beam. Modeling space is 3D. Type deformable. Solid. Base feature is the solid shape. Type is extrusion. Here it is 2000, and then I'll say continue. Okay. Now we have several functions over here where we can sketch the cross sections. So here I'll be utilizing this part, this function here, which creates rectangle. So I'll click onto this. Once if I click this, it will ask me a pick a starting corner for the rectangle. So my starting corner will be minus 5 comma 5. Enter. The opposite corner will be 5 comma 5, 5 comma minus 5. That's it. So this is my rectangle. You can, okay. Uh, this is my rectangle. Once the rectangle is done, press escape, and you'll get this popping up. Sketch the section for the solid extrusion. Press done. Now it will ask you depth. How much should be the depth? Depth is in this direction, into the plane or out of the plane. So what should be the depth? Depth will be the length of the beam. What's our length of the beam? The length of the beam is 200 millimeters. 200 millimeters. So let us give the depth as 200, which is by default, and say okay. Now you got the beam. Okay. So now you have the cross section was completed. The cross section details you have input into the ABAQUS, and you try to model the cross section here. Now the next step will be the material part. So let us go to the module, which is property, material property, and create material. this icon. I'm going to press this icon, which is create material, and again it is a steel member. I'll give name as steel. Then mechanical, press on mechanical, go to this elasticity, then elastic, click on elastic. Then you will be asked to enter the Young's modulus and Poisson ratio. So Young's modulus will be 200 GPa, but again, for the unit consistency, I'll be taking the units in terms of newtons and mm and seconds. Time is in seconds. So for that, it's Newton per mm square. So that will be 2 into 10 to the power 5 Newton per mm square. Poisson's ratio will be zero point 0.3. Then I'll click OK. Once I enter my Young's modulus and Poisson's ratio, I'll click OK. Now it has been saved. So next will be create section. So go to this create section. Now it will ask you which category does your section belongs to. It is a solid section, homogeneous, solid and homogeneous. So press on. If you want to name, you can name. You can name it as square section, homogeneous. Press continue. What does that section material or what is the material properties of that section? So here we only have one material property, which is steel member. I'll click onto this and say OK. Okay, now the section has been created. Now you need to assign that section onto this part. Okay, so far we have the part only. Part and material properties, both we are trying to define simultaneously, but we at the end we should also assign these material properties and sectional properties to this beam or to this part. So now you have this icon where it show which says that it is what is it saying? It is saying assign section. Click onto that and select the entire beam and press done. Now it asks you which section does this part has to be assigned. If you have multiple sections, then you will get a drop down where you have other sections also. But in our case, we have only one section, which is square section, and then you say OK. Now you get this color change. That means this has been assigned some section already. Okay. So far you are able to follow me. Burhan tried but not able to. Okay. Burhan and Abhishek, you are able
Yes,
to follow.
yes.
Abhishek, what about you? Software has some issue. Okay. Like, is it not? You're not able to open it, or okay? Like, if it is okay for you, can you share your screen? I'll just see if it was opening before. Okay. Is it the student license, student one, or with the student license or a cracked one? Okay. 2023. Okay. Fine. Then I'll continue. So we have this beam right now. It is assigned the section. It already has some material properties in it, and we have also given the cross sectional details to this beam, right? So the next step will be the assembly part. So yesterday, if you remember, I was telling you that if there are
Sir,
multiple
what about
parts,
orientation?
yeah,
What about orientation, sir?
yeah. Burhan, so if you remember yesterday our beam is linear one, right? It's a linear element. We are giving it as a line one. So in that line, you should always say that your cross section, you are just defining some cross section to that, and you are assigning that cross section to your line. But in this, you have already oriented your beam as a sketch itself. See, here you already have this beam oriented as per your own inputs. So here there is there's no need for you to orient your beam here. But in our previous case, you have a line, and onto the line you are giving some cross section there. So there you need, the software doesn't know about it, right? Because yesterday I was asking you about these two cases, uh, scenario one and case one and case two. This one and this. So software doesn't know. It only, you should tell the software that your beam should have cross section in this direction rather than this direction. But right now you yourself has created your beam in this way, and then you have extruded it. So that's why there is no need for you to give any orientation here. All
Okay,
right,
sir.
that makes sense, right?
Yes, sir. Okay, sir.
Yeah. So going next step is assembly. So assembly, if you remember yesterday, again we even today we have the thing one beam. So here again the assembly will be with only one beam. You go to this part, create instance, say square beam, uh, press OK. Okay. Then your assembly part is done over here. Fine. So what I was thinking is, see, this will be very boring. So what I'll do is I'll create one more part. Burhan, you just don't you just see what I'm doing. No need to do this part. Anyways, I'm not going to use this, but I just want to show why this assembly is actually there. Because even yesterday we have only one part, and you will not appreciate much about this. So you just see what I'm doing. For now, we'll continue again in 2 or 3 minutes again. So I'll just create one more part just for sake of showing you. I'll say it as a column, something like a column. I'll say okay. This time same, maybe 5. Yeah. See, now I have created one more part also. One is square beam and another one is a column. Both right now both have the same dimensions, but I'm just trying to tell you what actually in assembly tab what we are going to do. So when we go to assembly, we'll see both the parts which we have created. So now I have column here. So column is actually inside this because both are actually overlapping. So what we can do is I'll just show it. I'll try to. You can see it now, right? So here I have kind of, we have two parts. So when it comes, you can create multiple parts, and then you can assemble it in this tab, in this module. So you can bring those things here, and then you can assemble it, and then you can run the analysis. But in our case we have one simple beam, so that's why I'm not doing that analysis. I'm not doing that assembly part in this. So we'll just continue what we were doing previously. So now Burhan, you can start working on. So now we have done with this assembly where we have defined the beam here. Then we'll go to the step. We'll go to step, and again we'll create a step. So static general. So again, initial step is a static general. I'll go to static general, continue. I want nonlinear geometry switched on. So nonlinear geometry switched on. Incrementations. Incrementations. I will have some. You can give these numbers. Increment size this much, and maximum number of increments this much, and press OK. Okay, now you have also given your step or the type of analysis which you wanted. The next one will be load. Let us go to the load. In load, we have these boundary conditions. So what does the boundary condition? It's a cantilever beam, right? So one end is completely fixed. So you press onto this icon, and let us say it is fixed. Name, you can name it as fixed. Category mechanical. Go to displacement and rotation. Press continue. See, now when you press continue, it will ask you select regions for the boundary condition. So now you should understand, so far whenever you are doing all your analysis, we only deal with the line diagrams, right? It's almost it's like a line diagram. You'll just draw a line and you'll say whether it is a fixed beam or it's a pin support or if it is a roller support. But when you're dealing with a three dimensional beam, let me just see. So far whenever you have yeah, so whenever you are doing your structural analysis courses, usually you'll draw your beam something like this. So it's a line one, and you just say that it is pinned here and it's a roller here, and then you call this as a simply supported beam. And when you have a fixed beam, you'll say that this part is fixed, and then you call it as a fixed beam. But when you have a three-dimensional, if you want to draw this as a three-dimensional view, in three-dimensional view, in that case, what happens is that, let us say it's a rectangular beam, and you have some three-dimensional cross section, something like this. So now you tell me, where does this fixity has to come? Like, where the fixity is there. The same beam, let us say this is my, I'm working on this fixed beam here. I'm trying to draw it in three-dimensional view. Do I need to have my fixity only at this corner or only at this edge? Only at these edges, bottom edge? So where does the fixity occur, or where does the fixity act if I'm calling this beam as a fixed beam? Can anyone say?
On the face of the beam, sir. On that
Yeah,
face.
right, correct. All line cross sections need to be fixed. Yes, yes, yeah. So yes, so it should be on this face, entire face. Okay, and even here it should be entire face. Now tell me, if I want to exert some force, or if I want to impart some, say, dead load or live load. So in my line diagrams, what I do, I'll just draw a small line, and I'll call it as load P, and I say that it is acting at a distance of, say, some L by 2 or L by whatever it is. Let us say this is it. But in this case, like where it should act, let us say the same thing. The same thing is acting on this fixed beam, same load P. So this is my length, and this is my L by 2, the region where I have L by 2. So here, where should my load P act? Does it act at this corner, or does it act at this corner, or does it act at this point, or is it going to act at entire length L, this length L? So this is option 1, corner point. This is option 2, middle point is option 3, and line is option 4. So what do you think? Where should that P load P should act on that beam? Entire length, yes, yes, yeah. Load has to be distributed across the width. Yeah. Yes, 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 yes. Yeah. So you are right. So the load has to act along this length. Okay. If it is acting at this corner, then it is going to twist this beam. Okay. So always we consider symmetry in our loading scenarios, right? So it will twist this beam. So it can't act on this corner, even it can't act on this corner. We'll always assume that the load is acting along this line, or if it is very pointed, like it's like a very sharp kind of a load, like it's very pointed load, then we can place it on this part, on the central part, so that it will not induce any twisting on this beam. So right now we'll take this part that it is going to act along this length. Okay. So yeah, you guys are yeah, I think you are able to follow what I'm trying to say now. So we'll we'll apply the same thing over here as well. Now when I have created a boundary condition, it gave me this it asked me to select regions for boundary condition. So now I'll select this region, and I'll say done. Now you can see u1, u2, u3, ur1, ur2, ur3. So u1, u2, u3 are displacement boundary conditions. ur1, ur2, ur3 are rotational boundary conditions. So if it is a fixed, everything should be 0. So you can't allow anything. When you are not allowing anything, it will also resist forces in that direction, right? So you all these things you have to check it. So you have checked it, and then you by default it will give you 0 0 0 in all these cases. So once you have done that, you press OK. Now this is fixed. Now this is a fixed beam. Okay. Next, what is our next step? In our question, actually, you might think that I might have forgot to give the load acting P, but um, I wanted you all to solve without any load P. So what we can do is, see, in this case, what I actually wanted is, we will have some displacement instead of load here. So why we should always apply load boundary conditions? So we will, instead of this, we'll apply displacement. Displacement in vertical direction, vertical displacement. Okay. So how much vertical displacement we can go up to the D depth of the beam, that is about 10 mm. Let us apply 10 mm and see what is it going to how is it going to affect the moment generated over here, as well as the shear forces, and how the stresses are going to vary. We can see that. So now if you see again the three-dimensional view, I'm just drawing the top surface. So this line I'm going to exert displacement of 10 mm. Okay. So let us go back again. I'll click onto this create boundary condition. Now displacement rotation. Now I'll say that freehand. See, freehand doesn't have any displacements. Yeah, freehand doesn't have any displacement, but just for us to understand that I wanted to give some boundary conditions over here. I'm naming it as freehand. So here I'll say continue. So now I'll select this line only, the top line. Okay, I'm just selecting this top line, and then I'll say done. Now I wanted to give a vertical displacement, downward vertical displacement of 10 mm magnitude. So for that, I'll only click U2, and instead of by default it is saying as 0, right? I'll just remove it and I'll say -10. And rest of the things I'm just making it free, so it can have all the deformations in these directions if the if there is no resistance in those directions. So on this line, which is U2, I'm giving a displacement of about 10 mm downwards. So minus, because again, if you remember yesterday's session, we were discussing that positive y is in upward directions and negative direction. Yeah, negative y is in downward direction, so -10. So now you can see these arrows popping, showing it downwards, which says that you are applying a deformation or a displacement in downwards, which is downwards. So now I don't have any loading boundary conditions, so no load boundary conditions, force boundary conditions are not there. So now we have given this. Next step will be the meshing part. So let us go to the mesh. So now we have to be very careful because we only wanted to get we wanted to have only 1,000 nodes, right? So this is 200. The beam is of the beam is having a length of 200 mm, and the cross section is 10 by 10. So let us have Burhan. Now we'll again have a different mesh sizes. So I'll just try to. Oh, actually, I can have any mesh size, right? So I'll go for a very finer mesh. Not very, but I'll go for a. So again, this thing popped up. If you remember what I was doing, because yesterday, if this thing pops up, I need to, instead of selecting this as assembly, I need to select part. Okay. Then select seed. So Burhan, you can go for a mesh size of 200, right? So you can go for a mesh size of 20, 200 by
Okay.
10.
Okay. So
Uh,
200 I have.
uh, yeah, 200. Yeah, maybe you can go for it. No, no, but see, but the depth is only 10 mm, right? So in that case, okay, we'll do a different kind of a meshing now. Maybe that will be. I'll show a different. See, we so far what we are doing is we are doing a global. We are giving an entire mesh of 10 mm size or 20 mm size, right? So now what we'll do is, in length direction we'll give one mesh size, and in depth direction we'll give you another mesh size, so that we can have different mesh sizes in different directions. So instead of having a square kind of a mesh or a cube kind of a mesh, we'll have a cuboid elements. Okay, so for that you can see the seed edges. Now you can click on this seed edges, and you only click the length, not the width. So even see these parts, you don't click it. These parts you don't click, only click one, the length or the edges of this edges of this beam, and press done. So in length direction what we'll do is we'll have uh, I can have maybe 10, and Burhan, you can have you try to have about you try to have a mesh of about 30
Sir,
or
I can select only one length size, sir, in the software.
sorry, one.
In only one direction, sir. It's only selecting one part.
Okay, so okay, fine, fine. Then yeah, we'll just okay. Then we'll do the same thing. So, uh, Burhan, you can take it as 20 here. I'm going with 10. Okay,
Okay.
then otherwise I'll go with 5 because 5 and 20 maybe you will have some differences in your results that we can try to appreciate once we if we have some variation between this. So I'll go for a very smaller mesh. So 5 mm, I'll say apply. See, in 5 mm, I'm only having two elements in thickness direction. Um how many elements you are able to create, Burhan? You try to check, mesh it also. See, you can see a number of elements created here,
Uh, it's not showing me, sir, number of
but
elements.
you are able to get the mesh, right?
Where we have to
On
get, sir?
this mesh, you are able to get it. Like you are able to see this kind of boxes.
No. Uh, yes, sir.
Okay. So
I
can
got
you
it.
tell me? Yeah, can you tell me in depth direction how many boxes you have?
I don't have any boxes in the depth direction, sir. It's
Right. So
only
that then there is no point of doing this entire thing. What we'll do is we'll try to reduce the mesh size and check. You do one thing. Maybe we'll put a mesh size of 2 mm. Can you put a mesh size of 2 mm?
yes,
You are able to get it.
yes, sir. I got it.
You are able to get this elements also, right? Like you are able to completely mesh it.
Yes, sir.
Okay. Can you tell me how many elements you have in depth direction?
5, sir.
5 boxes, right? Okay. So two is also working. So fine. You go with two, then just curious. We'll also try with 1 mm. You also try to do with 1 mm. Because see, 25 elements itself is like too big a number. I don't think 25 elements can hold about 1,000 nodes. But fine, we'll see what is it going to do for a one element size of 1 mm. So go for 1 mm now. You can delete it. You know how to delete, right? See,
Yes, sir.
you need to press this part and hold for some time. Then you'll get these three popped up. Then you can say you can use this delete option here. Okay.
Yes, sir.
Try to give 1 mm and check.
20,000 elements have been created.
Oh, then it's perfect. Then you are able to get as many elements. But I don't know whether it is going to analyze it or not. Fine, that we'll see. We'll see what if it is going to analyze it or not. So now again for us to have some discrepancy, you go with 1 mm mesh size. I'll go for a higher mesh size. I'll go for a 5 mm mesh. 5 will not work. 3 mm mesh. So three. See, I have only three in this direction, and this is a very coarser mesh. So yes, now mesh is created. Burhan has about 1 mm. 1 mm has his mesh size, and I'm having about 3 mm as my mesh size. So meshing is done. Next one is create a job. Go to job, create job, square 3D beams. Yeah, continue. Press OK. Go to job manager and submit.
So it's not analyzing, sir. Saying it's restricted to 1000 nodes.
Okay, wonderful. Yeah, then you go back to 3 mm.
Okay,
I'll 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 do I'll do a 1 mm mesh size. You can go back to 3 mm.
okay.
You're able to submit. Are you able to submit the analysis?
Sure, sir. I'm on the way.
Okay.
I'm doing.
Okay. Okay. Try to submit it. I'll come in 2 minutes. I'll just get some water. Yeah. You're able to submit it.
No, sir. I have tried doing it with 4 mm.
Okay. Even 3 mm is not working.
No, sir.
Okay.
4 mm is submitted, sir.
Okay. You got your results as well.
Yes, sir.
Okay. You can go to this result tab. So how's your contours looks like? Similar to this.
Yes, sir. It's similar.
So if you remember again, I'm just telling you, we have this uh, the stress contours, right? What are those called? The lines joining the points having same stress. So if you see these contours, right? it's something like this. It goes somewhere in this, and on the bottom again here, and on in the middle you have almost zero stress levels. So what is your maximum S mises? For me, it is 683.
530.
Uh, it's 530. Okay. So what's your U value? U should be the same. You because U is our input, so U will be 10 only even
Same.
for you. No, it will be the same because we have given it as 10, right? So it will be
Yeah.
10. It will be the same. And what might change is the values in between. Okay. Maybe if you want, okay, we'll see the cross-sectional properties first. We'll also see what's happening across across the cross section. Now, yeah, this is my cross section. So yeah, so in cross section, if you see,
So how did you change the view, sir? View of the
can
photo?
you are able to see, you are able to get these things here?
No,
Do you
sir,
have
it's not
this?
there.
Okay, if it is not there, you need to switch it on. You go to this tab, view tab here,
Yes.
and then go to toolbars,
Yes,
and then click on to this views. Views has to be ticked.
yes, sir, I got it.
Yeah. Then you can play with these icons. Then you will know which direction you wanted to check. So see, this is my fixed cross section. I mean the fixed where we have this fixed support. So what I'll do is I'll just see S11. See how beautiful it is. See, S11 is actually my longitudinal stresses. So my longitudinal stresses for a cantilever beam, where do we have positive, I mean tensile stresses, and where do we have a negative? That is compressive stresses, top or the bottom. Top will have a tensile stresses and bottom will have a compressive stresses, right? So you see when you are rotating, when you have, see your beam is actually bending in this direction. So the top has to experience tensile stresses. So you see the top is experiencing the tensile stresses, which is this much, and the bottom is experiencing compressive stresses, which is this much. And as you go along the depth, it goes from plus 210, or let us say 211, and then it goes to 0, and then it comes back to minus 211.1. What about you, Burhan? What is your values for S11?
So it's 807.
807.
Yes,
And what is in the bottom?
it's the same, sir. 807. Only
Okay.
the middle values are changing.
So
It
you're
is going
checking,
from
you're
minus
check
8 to 2, plus 1 and 8.
minus, sorry.
Minus 807 to, it's going in the minus direction and it's changing to plus.
Okay. Are you checking S11 only?
Yes, sir.
Yeah, that is actually a very um, that's a very good observation as well. See, here I'll explain the reason why we are getting very high values to Burhan. Before that, we'll see some differences. So let me note down those differences here. So Burhan has a mesh size of Burhan has a mesh size of
4 mm.
So S11 maximum I was having about 210, and Burhan, how much? 807.
Yes, sir.
807 MPa, which is too high actually. And what is the other one? So what we can do is we can also check the reaction force. What about your reaction forces? How much it is it showing? You can, we can have magnitude. Yeah, even magnitude is also fine. Yeah. How much is it?
272.
272.
Yes.
Okay. So reaction forces are, so these are actually not the reaction. The see, usually when we say reactions uh, in our analysis, so where is that? Yeah, see, in this, when we say reactions, what we mean is this reaction, right? But right now, the abacus is not showing this reaction. What abacus is showing is reaction at each nodes. Okay, it is showing reaction at each nodes. So the number of nodes along this path multiplied. So we need we are getting an, each node will have one reaction. When you sum entire nodal parts or nodal reactions and then consolidate it, you'll get one reaction force, which is the final reaction, which is this reaction. Okay. So this difference between Burhan's value and my value is because of the mesh size, because Burhan is having about, so I'll just draw the cross-sectional view of both of our beams. This is my beam and this is Burhan's beam. So how many boxes you have? Only three, right? Burhan, do you have only you have only three boxes in this direction, right?
Yes, sir.
Yeah, but for me there are several. Like I have about 10, I think. One, two, three, four. Just assume that these are 10 lines, and I have another 10 lines in this direction. So I have about 10 by 10, 100 nodes only in this, and Burhan is only having one. These are four and four, so 16 nodes. Okay, so he's having 16 nodes and I have 100 nodes. So the nodal values, each nodal value corresponds to each reaction forces. I'll tell you how to integrate this and get a final reaction force, but right now he's having some reaction force that we'll try to integrate it, and we'll compare those values. Next what we'll see is we'll try to see U values. Okay, U, or we'll try to see LE. LE is nothing but the strain values. Strain, how much strains you have. So what about you, Burhan? My maximum strain is about 0.00361. And what's it for you?
Sir, 261. 0.00261.
You're checking the maximum principal strain only, right?
Yes, sir.
Okay. So this is my LE. LE is nothing but strain, elastic strain. For me, it is 0.0036. And what's it for you? 0 point?
0.0026, sir.
Okay. Now, what I need is, why do we have differences for different mesh sizes? So, Burhan, do you have finite elements in your coursework, UG?
No,
Introduction to finite elements or
no,
any of
sir.
such? Okay, fine. Okay. Usually, MTech students, I think you might be studying this part, right? Like when you're studying finite elements. So when you have, let us say, when you have more number of elements, so this is your nodes, and if you have only two elements, here you have this is entire beam and you have only This is element 1 and this is element 2. Okay. And when you compare with the same beam having several elements, 1, 2, 3, 4. In this, there are 4 elements. So always the beam with lesser elements will be stiffer. Okay. The beam having lesser elements, so coarser. So lesser elements is nothing but coarser. So coarser mesh, then you are going to get stiffer response. Okay. So if I can also, I hope you know about this, but I don't want to again explain why coarser mesh is having stiffer response. I hope you already studied about this. And finer mesh will have a flexible or less stiffer or less stiffer response. So what does stiffer means? So stiff means higher loads and lesser deformations. Okay. Just for you to just I'll try to give some hints. So it is something, you can assume some a chain or something like that. So let us say you have multiple, let us say you have constructed see, these things are straight parts and you have one link over here, and you compare with having a one straight rod and you have only one link in between. So you can simply imagine, right? You can get that analogy that lesser, more the links, the flexible will be the system. Less the links, it will be more stiff. Stiff means it is going to take a lot of load and the deformations are going to be lesser. So now let us bring this concept here into our analysis. Okay. Now stiff means higher loads, I said, right? So now this is Burhan's beam and this is my beam. So Burhan's beam has a stiffer response. That means for a given deformation, what is the given deformation? We both have a deformation is 10 mm. For given deformation, Burhan should have a stiffer response. That means his loads should be higher when compared to my loads. Okay. If the loads are higher, stresses will be higher. And if you see, Burhan is having higher stress. Okay. You see, he's having almost like 4 times stress when compared to my beam. And which one is actually the correct way of doing, or which one is the right way, or which one is then whose result uh, should we trust on? So let me let me just get one more slide. So I hope you are able to follow what I've said, right? So coarser mesh is stiffer. Okay. Stiffer means more loads. More loads means higher stresses. Finer mesh means less stiffer, less loads, so smaller stresses. So in practice or in practically, if you have the beam can have infinite number of nodes or infinite elements, because you can break down the beam into infinite elements. Because we wanted to do a simulation which is again computationally efficient, or computationally it has to be cost effective computationally also. That's why we always consider some finite number of mesh size or some finite number of elements for this analysis. So how do we know, or why, how can we say that whose results are to be followed? Because Burhan was getting stresses of about 807. So with this stress, if he's going to design the beam, then he's going for a very conservative design. And in my case, I have about 1 mm mesh size. I can even go for another mesh of 0.5 mm, and even also 0.25 mm, and can check. But whose results do we need to trust? So for that, what we'll do is we'll do a mesh convergence study. Okay. So what is mesh convergence is, when is your mesh converging? So what we'll do is, this is my plot, XY plot. In x-axis, you will take mesh size as your variable on your x-axis, and in your y-axis you can take any output variable, or most, like, usually we'll take deformations, or like S mises, maximum S mises, or S11, whatever it is. So in current case, let us take S11 as my uh, S11 as my Y variable, and mesh size as my X axis, and S11 will be my Y axis. So let me plot. I was for my mesh size 1 mm, I'm getting S11 as 210 MPa. Burhan, can you try another mesh size of 5 mm? Meanwhile, try with 5 mm,
Okay,
and
sir.
you can also try with 5 mm, and after that you tell me the results. Then we can go for another one also. Okay.
Okay.
I'm just meanwhile I'll just write down. Yeah. So mesh convergence. First one is, so this will not be to the scale, but just imagine that it is to the scale. I'll try with another one with zero point 0.5 also. That's why I just mentioned here 1.5 to 2.5, and this will be 3, 4, 5, 5, 6, 7, 8, 9, 10. Okay. So my values for one is, how much did I get? 210 MPa. So I'm just marking it somewhere here. 210 MPa. And Burhan's is 4. And 4, the value was about 807. 4, the value was about, so if this is 200, 4 times this is somewhere here maybe. So this is something like 807. And let me try with, I'll try one more mesh size, and Burhan is already trying for 5 mm. So let me try with another mesh size. I'll just copy this so that it will still be with me. I can copy this model also as a, so what I can do is, I'll right click here and I'll say copy model. So here I'll just say that I want to go for 0.5 MMS. So I can generate a new copy so that I'm not rewriting what I have done for this, for my first model. I'll go to this model, mesh, and in this I'll remove the existing mesh. Mm, okay, column is not having any mesh here. Yeah, I'll remove the existing mesh, and I'll give my mesh size as 0.5 mm. This is very fine. We can't even see. Okay, so it is 0.5 mm. Then I'll go back to the job. I'll create a new job, 0.5 mm mesh. Continue, press OK, and submit. This will take a while because the elements are too many this time. So it will take a while. Meanwhile, I'll just get back to Burhan. Burhan, are you able to get the values? You can
Um,
give.
so I have submitted the analysis.
Okay, fine. Yeah, why the max? Yeah, Raghu is having a question. Meanwhile, I'll just try to answer it. Why the maximum strains at top and bottom of cross section are not equal to each other, since we are getting maximum stresses at top and bottom are equal. So Raghu, if you see my, it all depends on your mesh thing first. So I'm just going back to my results. So if you see here, you are saying that why the top and bottom maximum strains. Okay. Okay. See, these are maximum principal strains. So if you know the concepts of principal strains, you know what it does, what it means, right? So I'm not checking the longitudinal strains which you mean. So here you can see these are almost same. LEI11 is nothing but the longitudinal strains which you are actually referring to. But the initial strains which I was comparing is my maximum principal strains. So maximum principal strains, if you remember, you have the concept, right? So you have sigma x, sigma y. So I just don't want to. It's a 3D matrix, a three-dimensional matrix. So you need to solve for you need to solve for the eigenvector, right? So then you'll be able to find your three principal stresses. So this is a maximum principal stresses which I'm talking. I hope this is clear. Yeah, yeah. Let me check if my analysis was done. Yeah, it is still running. I think it will take some time. Before that, what we can do is okay, let it run for some time. I'll also show you some other options in visualization tab. So first thing is we can also break down at the middle of the cross section over here and see what are the stresses at that point. So for that you can use this view cut. I'll cut it. You can see now I have cut this section into half, and you can see how the stresses are varying along this one. But see, we are not bothered much about uh, uh, the results in these planes, right? So usually we are bothered about what's happening inside the cross section. So right now we already have a view on the fixed support, and I just want to know what is happening at this mid of this support. So for that you can use this view cut manager. Go there, and you can see right now it is cut about explain. So explain, whenever, if you remember the planar or the coordinate geometries, whenever we are learning our mathematics, right? So we'll always when we say it's an explain, that means it is perpendicular to that plane. So you have your unit normal to that plane, or to that, sorry, x plane is nothing but it's the x-axis, the normal, which is the 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 unit normal, which is passing through that plane, right? So x plane is nothing but x-axis, the normal to the x-axis. So this is my x-axis. Normal to the x-axis is nothing but yz. So it is in yz plane. But right now, what I want is z plane, because I want xy plane. I want to see what's happening in these planes. So I'll click onto this z plane. Now you can see what's happening there. So now you see here. Fine. You can keep on increasing or you can keep on decreasing. You can go back to any frame where you wanted to see your stresses, strains, or deformations, and at each section you can see how the stresses are varying or how the strains are varying. So I'll just go with SMISIS. See, you can always check. Okay, this is one part where you can visualize what's happening inside the cross section. Fine. And let me check if the job was what is still running. Let me kill it. I'll run it again. Yeah, so this is again something new which I wanted to tell you. So far what we are doing is uh, when we are submitting a job, right? What we'll say is we'll just go to we'll create a job and we'll say submit. So instead of that, if you have knowledge about your system, your laptop, and if you know how many cores you have, so this is the thing which actually pops up. You can go to this parallelization, and let us say if you have a multi-processors. So usually I think in my laptop has about 16 processors, I guess. So right now you can keep increasing. So by default, it is only two processors. So two processors is like it takes more time to solve some problem. But if you are using maximum number of processors, then it will solve slightly faster. Not slightly, like it's almost like proportional. So right now I'm giving 8 processors because I don't want to use entire processing speed to only this part, because now I need to even run my WebEx also, right? So that's why I'm just giving 8 processors here, and I'll say okay, and then I'll say submit. Now it might run fast. Uh, Burhan, meanwhile, what's your status?
It's done, sir. I can tell you
Okay,
the values.
sure. Yeah, tell me the values for 5 mm,
Three,
right?
yes.
Yeah, how much is it?
S11 is 364 MPS.
364.
Yes, it's decreased. It
Okay.
decreased. Reaction force are 460, sir.
Yeah, it will decrease because now you have no, it did it increase or decrease reaction force? How much was the previous one?
It was 272, sir. Now it increased to 460.
Okay, but yeah, this decreasing is like, yeah, this is not giving me any trend. But anyways, yeah, we'll just plot it. So it is 364 you're saying, right? So let me plot it. 364 for 5 mm. So it is somewhere here. Okay. Then in my case, let me check. So I'll also run one. Can you run with one 10 mm mesh size?
Okay, sir.
Yeah. So meanwhile, we'll also see. So now I'll show you how to see the entire cross-sectional reaction forces. So we are talking about reaction forces at this phase, right? If you want to see the reaction forces at this phase, yeah. So at this phase, we wanted to see how much will be our reaction force. So What reaction I want to see? I want to see my vertical reaction in this direction. So for that, I'll go to this create XY data, and I'll select ODB field output. I'll press continue. I'll go to integration points, or you can see this position integration point. Instead of integration point, I'll select unique nodal. Okay, there you'll get reaction force. You can select this reaction force. RF1 is in X direction. X is in this direction. RF2 is in Y direction. So we want Y direction reaction forces. Then go to elements. Now it will ask you to select your elements in this module, element nodes. Here, go to this selection and you need to select your elements. So you press on this edit selection, and here you can select. So before you select, you just align this, and then you can select all the elements in, okay, not this way. Yeah. So you can select your elements, all the elements this way, and press done. Now you can see 22 element nodes were selected. Okay. So for this version, I think for 2019 version, you don't have summation value. You can directly sum these 22 nodes values, and you can get a final plot. But I think some other, I think another student, I think he might have installed some other version, right? So he'll be getting this sum plot. So right now what I'm doing is I'm just saying it as save. Okay, and it was saved, and we can also plot that. I'll just try to plot it. You can see how it is plotted. When see you have all these things have been plotted. So your final values are nothing but when you sum when you add all the values of these the values of reaction forces at all the nodes, and when you consolidate it and when you add all the things cumulatively, that is going to give you your final reaction force. Burhan, do you get this save for all option? Can you try that? See, right now I was getting only this save option, right? But for a latest versions, usually you will also have a sum version. You can also do a summation of all these nodes.
Sir, actually, I was analyzing with 10 sir, so I
Fine,
didn't.
fine, fine, fine. Fine. Okay, we'll do it again. I'll ask you to do it again. So I think my other analysis got over. Let me check that. For 0.5, we'll see what's the results. So now for 0.3, you see the S mices. We'll see S11. S11 is 263.2 for me. 53.2. Okay, what is the 263.2? Okay. Yeah, what is it for you?
Sir, for
Something.
10 it's 747.
Again, it is increasing, right?
Yes.
Yeah. So now you can see that there is basically, actually, there's, to be frank, there's no trend. If I join these points, it is increasing. Here there's a decreasing, and then maybe it is increasing here. So now there, if you want to say that which values they are converging, you're not able to figure it out right now. In here, at this point, you say that this value is slightly higher than this value, but this is very higher than this value. and again it drops here, and again it is almost higher. So in these cases where you have so much of variation in your convergence, like see usually what does convergence means is, once you plot what happens, you will get, let us say for higher mesh sizes, you are getting a very high values, and after some time the values will remain almost the same. So what we'll say is, at this mesh size we'll say that the plot is converged. So from here onwards, you'll be getting almost the same values. So usually we'll choose this mesh size as our actual mesh size of our plots. Mesh size, sorry, not for the plots, for model. So in this case, right now we have a very unusual kind of a variation in our mesh convergence. So for that, to check, we need to do one mesh size over here and another mesh size over here, and maybe we can check with 6 mm mesh size, and we can also check with 3 mm mesh size. So if we know about these 2 points, then we'll get some trend. So we'll say that at these points the trend is, it's it's almost the same here, it's a higher, the values are higher, and as our mesh size is reducing, the values are almost trying to converge. So once it is converging, then we'll take this as our mesh size. So fine, we can do one more trial, but I think let us do one more trial. Burhan, maybe you can try with 6 mm. I'll try with another 0.25, but 0.25 will take a lot of time. I'll try with 2 mm. I'll try with 2 mm. Burhan, you can go with 6 mm. Or if you think that it is okay, you are able to understand what I'm trying to say, then it's fine. We can just see some visualization tricks, and then we can go ahead for another analysis. So just I'll just repeat what I was telling about mesh convergence. So let us say if I have, so how do we finalize our mesh sizes, okay? So before we come to any conclusions for our analysis, we'll keep running for some mesh sizes. So why can be any parameter. So in our case, we are taking S11, and x-axis is mesh size. So we'll we'll try to do analysis for different mesh sizes, and maybe as we keep reducing, we'll get maybe something like this. Okay, this will be how our plots looks like as you're going for mesh sizes. So let us say for a higher mesh, you have very high S11 value, and when you keep on reducing your mesh size, your values are almost near to each other. So now my question is, in this case, we'll say that this is my mesh size which I wanted to consider for my analysis. So let us say this is 2 mm mesh size. So now can anyone say, see, even here it is converged, right? Here it is converged. Let us say it is 0.5 mm, or maybe here also it is. Why can't we take these mesh sizes, or why can't we take, see, here also you have some kind of a convergence happening here. So let us say this is 10 mm. So why can't we take mesh sizes of this order And why can't we take mesh size of this order? Why we should take only mesh size of this one, which is 2 mm? Can someone try to answer? What happens if we take very finer mesh? From the mesh convergence analysis, what we got is we got only 2 mm as our mesh size. Fine enough. But what if we are going to take mesh of very fine size? What happens? So mesh size of this order and mesh size of this order. I think you have already seen what happened to my two less sizes is time consuming and large mesh sizes gives inaccurate results. Yes, yeah. You have already seen, right? Like when I was using mesh size of 0.5 mm itself, it took about 10 minutes for my computer to solve that problem. So if you're 2 mm and 0.5 mm, let us say in this case, if you are 2 mm and all and your 2 mm and your 0.5 mm is almost giving you the same values, then why you should waste your time by running your analysis for longer time when you are getting the same kind of results for this 2 mm also. So this is kind of an optimized mesh size. So it is optimized mesh size. So what are you optimizing here? You are optimizing your results. You are optimizing your results, and you're not optimizing your results. This is wrong. You're optimizing your computational time. Computational time and results are nearly accurate. Okay. So that is the reason why we have to do some kind of a mesh convergence studies before we do any analysis. I hope it is clear. Like, I hope you're able to follow what I'm saying. Any doubts? Burhan, do you have any doubts? You're able to follow?
So once can you try with 7 mm mesh size, sir? Just I want to compare the results, sir, if it's same or not.
Okay. You want the mesh to be 7 mm, right? See, if it is a 7 mm, right, you are not able to get, you will not be getting any uh, variations or contours in depth direction, because in depth you have only one element. So element you'll only get strains in the element. The strains or the stresses in the element will be constant, so you will not get any variation. But anyways, I'll check for this also. This is model one. Yeah. What's your results? S11.
Sir, I'm
S11.
getting a different values.
No, no, no. I think maybe I might have missed something. This doesn't this doesn't look correct. What's your values?
Sir, it's different.
No, like what's your value?
U is the same, sir, but strain is like 5.87 E.
5.87.
Yes,
5.87 e to the power how much?
-0.7, sir.
Okay. With the same mesh size, 7 mm.
Ye- Yes, sir.
You also tried with 10 mm mesh size, right?
Yes, sir.
So your E values and G values, I mean the Poisson's ratio and your E values are same. E is 2 into 10 power 5 and your Poisson ratio is zero point 0.3, correct?
Yes, sir.
And your beam cross section is 5 to 100 10 mm by 10 mm.
Yes, sir.
Yeah. Then why it should be different? See, there's no, there is any strains actually. Even in this case, if you see, my strains are like, what is your S minus for your case? S minus maximum
It's same, sir. For 10 mm, it's the same.
0.136.
Yes, sir.
Okay, but for 7 mm, you're saying that it's different, right?
Yes.
But 10 mm, you gave me some different value. You gave me something like 747 something.
Yes, sir. It was 747.
No, right? It is 0.007457, I guess.
Yes, I made a
Yeah.
mistake.
Yeah, yeah. That's what. See, once your element size is higher, right? Now in this case, it's almost like it's like a linear kind of an element. See, your beam itself is having one element in this direction. Then your analysis is not going to give you any accurate results. At least in the depth direction. From this, the learning is at least in depth direction you should have at least two or three elements. Only then you will have a uh, closer to the accuracy or closer to accurate results. You understood what I said?
Yes,
I'll
sir.
try with 4 mm. You tried with 4 mm also, right?
Yes.
Let me check that 4 mm also then once. This is how your 4 mm looked like, right? 4 mm, three by three boxes. Yeah. What about your 4 S11? You said, oh, it is 80.72. It's 80.72, right?
Sir, I was confused in that unit conversions.
Okay, okay, fine, fine. Fine. Then this should be like 80.72, and in other, what is your LE? LE11. This is about 7.47. Even that's okay. You're checking for the maximum principal strain. Yeah, this is okay. This is at least this is matching. Fine. So can you check this part where you can draw this XY data? I'll tell you how to do that. Go to your visualization, create XY data. Go to this, check this ODB field output. Say continue. Now go to this reaction forces. You are able to see this?
Sir, I can't see reaction forces here.
No, no. You go to this position, and here you need to select unique nodal.
Yes, sir, I got.
Then you see reaction force. Then
Yes.
check this box RF2. Okay.
Yes, sir.
Then go to elements and nodes. Fine. Then click onto this edit selection, and then you can select these nodes. You're able to select these nodes.
No, sir.
You need to so you are able to see this part at least.
Yes, sir.
So you go to this edit selection, click onto this edit selection,
Yes.
and change your view. Your view has to be in this what do you call YZ view.
Okay. Sir, I can select only one at a time.
No, you need to do this way. You can drag it, and then you can select these nodes.
And
Done.
what is that viewport, sir?
Uh,
XYZ.
y, it's YZ.
Why is it?
Or fine, you can select one at a time also. That's okay. Then you select one at a time. So you need to press press shift, and then you
And
select these nodes. Yeah.
so I've selected the notes. Now what?
Yeah. Now press done on the bottom. Yeah. Can you see? Do you have any other options rather other than save here?
Save as. That's it. You don't
Ah,
have
ah.
save.
No, no. You say you press that save as,
Yes.
and what did it like? What can you see now on the screen? What all can you see?
Save operations are XY.
Yeah, you scroll it down. Maybe you'll find something called sum or something
Yes.
like that. Summation.
Yes, sir.
Yeah, you click onto that sum,
Okay,
and
sir.
you can plot.
In plot. Yes, sir, I got.
You got one single line, right?
Yes.
What is the final value like after like uh, can you tell me what all you see in your XY plots? You can see force versus time. Am I
Yes, sir.
right?
Force was.
So can you tell me at time 1 second what is your force value? You can click onto this tools here, go to query, and go to this probe value, and then you
Yes.
can see this nodal value there.
Yes. I got two lines, sir. Actually, I selected two nodes, and
Oh,
I got
yeah, okay,
minus 169 for one node and 114 for one node. Other node.
okay,
The
okay, okay,
maximum is 114.
okay. Fine. Like what I wanted to tell you is that you can also it can also sum your values, and then it can also give you your reaction forces. That's what I wanted to show. You can try it later if you wish to.
Okay, sir.
Okay. Yes. Yes. Today again, just to recap what we have done, we started with three-dimensional elements. We have given the cross section, and then we try to give our boundary conditions. We tried to do some mesh convergence today. Again, if other students have installed it, it would have been much more easier because each student would have done one mesh size, and then we would have consolidated those data, and we would have got some convergence there. But now it's only about between me and Burhan. Then we had to skip some steps for mesh convergence. So again we understood that the importance of mesh size in our analysis. Mesh size is very important. How do we choose it? We need to perform mesh convergence for it. We also saw some visualization tools where we can see different types of how like where we can view different types of stress values, strain values, etc. And we also saw some contours, like for I'll show the contours for my job where I have done it for 0.5 mm. You see how beautiful the contours are. So this is how the S minus contours looks like, and even S11 you can see. Basically, S11 is so small, that's why it's not giving up. But S minus, you can see how the contours are. The maximum contours goes something like this, and over here, and at the middle, the contours are zero. That means there is no stresses happening at the mid cross sections. That's what it means. So we are able to visualize the contours. We are able to see how much the displacements are. Uh, we can also actually plot load here versus displacement as well, or reaction force and displacement plot here, so that we'll also know how much the displacement like that how much displacement for this cantilever, how much load is required to give a displacement of 10 mm at the free end of this cantilever. So that is another part. So uh, we can also sum up all the reaction forces values, and to get a one generic uh, reaction force which is acting on this uh, fixed support or the fixed end of this beam. So yeah, these are the learnings of today's class. I think I'll stop I'll stop now and I'll take some doubts if you have. Uh, yeah, if you have any doubts, I'll take. You can ask me now. Any queries, doubts, comments?
I think that there are no doubts, Professor.
Yes. Yeah. In
Sir,
that case, yeah, Abraham, tell me.
once again, can you tell me the mesh convergence? How to choose the optimum mesh
Yeah,
size?
yeah. See, usually what happens is that if you have multiple mesh sizes, right? Here, right? What you do is like, maybe you can take that as a exercise. Now you go back, but see, for you, the limitation is you can only start from 4 mesh size, right? Even 3 is not working for you. So what you do is what's the actual procedure? I'll tell you. So this is the actual procedure where you have this x-axis and this is your y-axis. Sorry, this is your x-axis. In y-axis, you can have any parameter. So it can be your reaction force, or it can be your stresses, or it can be your strains, longitudinal strains, or it can be your deformations. Here in our case, it's U2, whatever you choose to be. So, like for example, if it is a column member or if it is a beam member, usually what we consider is we'll consider it as deflections over here. Deflection. Let us say this is U. You are applying some load P and you are trying to see what is your final displacement, uh, U max or U max or U2, whatever it is. So you pick on one parameter which is very important for you. So let us say if you think that your reaction forces are important, you can pick that parameter, and you can keep increasing and decreasing your mesh size. You start with some values and you can do you can keep plotting your values of this parameter with respect to your mesh size. Usually what happens is that if it is your deformation or if it is your stresses, what happens is that there will be one trend. There'll be one trend. Either it will be something like this, or it will be something like this. Okay. So or it will be something like this. So in both the cases, in this case, in this case and in this case, what we need to understand is at some point your values are converging. So in my in case 2, I'm calling this part as case 2 and this is my case 1. In my case 2, even if I'm decreasing my mesh size beyond this point, my values are almost remaining constant. That means even if I go for a very smaller mesh, I'm going to get the same results or similar results. So why why I should why I should spend a lot of computational time in going for a smaller mesh and to get the same kind of a results which I'm going to get at this point. And also, if I'm going to go for a higher mesh size, here my results are always varying. My results are varying and varying all the time. That means these are not constant, and then these are inaccurate. So that's why I'll choose this optimized point as my mesh size for my actual analysis. And even if you see this red plot, which is case 1, here also at maybe let us say at this point the values are converging, and after this the values are almost the same. So I'll say that this mesh size is my converged point. So I'll choose this as my analysis mesh size for my analysis. So now you understood, right?
Yes, sir, got it.
Okay. Anything else?
No, sir.
Yeah,
Others?
okay, sir. I think there are no questions.
Okay, okay, sir.
Just
Then.
take Deepti, any questions?
No, sir.
Yeah, okay. So thank you very much for this, sir. Again, tomorrow is the coupon shell element, experiment, right?
Yes, 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 yes.
Okay. So again, we'll meet tomorrow at the same time, 7 to 9.
Sure, sir. Sure. Okay. Okay.
Thank you. Thank you, sir.
Okay. Thank you. Yeah. Bye.